Okay, so let us maybe start. So last time we considered Rosar algebra with this commutation relation. And also a free boson algebra, Heisenberg algebra. And representations of representation of this algebra was at the level n, alpha 0 n, was a span of vectors a minus n1 and so on, a minus nk, acting on a vacuum alpha. And in this case, h delta was a span of L minus n1, L minus nk, acting on vacuum delta. And now, so by the way, this representation is called Fock module. And this is called Verma module. Now, the question is, what can be the structures of such representations? Like, do they have sub-representations, for example? How and how all this works? So. For example, let us look at the case, and we know that in principle sizes of these modules are the same. But let us consider the following example. Let us consider an example with delta equals to 0. It is also called vacuum Verma module, or vacuum module. So what do we have here? We have delta, we have L minus 1, we have 0, L minus 1, 0, 1, 0, L minus 2, 0, and then L minus 1 cube, 0, L minus 2, L minus 1, 0, and so on. Now let us ask, can we have some sub-representations of in this Verma module, some subspaces which are closed under the action of the Verma algebra? So remember that mm, a highest vector condition tells that Lk when k is greater than 0, acting on a highest weight equals to 0, and the L0 delta is so it's an eigenvector for L0. This is highest vector. Uh, let us act with uh, let us take this state and act on it with Lk. Lk acting on L minus 1. Well, this equals to what? This equals to k plus 1 L0 acting on vacuum plus L minus 1 Lk also on 0. And well, we see this is 0 because dimension is 0. And this is 0 because LKs act by 0 on this highest vector. So we see that there is highest vector which is a descendant of highest vector of this Verma module. So we have the following picture. Well, this is our Verma module. And here, so it's a 0 level where we have just 0. And here we have L minus 1, 0. And it turns out to be also highest vector of the Verma algebra. So we see that there is a Verma submodule here. And it will and we can try to ask now what is the structure of the submodule. Is it reducible, or it also has some submodules? So in this case and by the way, if we want to construct a reducible representation of the Verma algebra corresponding to this highest weight, we should take our Verma module and factorize by all submodules. Hmm? Yes, thank you. I was too fast. So when k is equal to 1, it is 0 because it is L minus 1 acting on 0. When k is 2 and higher, it is 0 because it is just LK acting on 0. Sorry. When k is equal to 1, it is also 0 because it's L0. Because L0 acting on vacuum equals to 0. Mm. Hmm? Uh, yes, we check this for k greater or equal than 1. Greater or equal than 1. So we check that this vector is killed by all, well, better to say k greater than 0. We check that it is killed by all positive k's. So it is highest vector of with respect to the action of the Grassor algebra. Mm-hmm. Mm-hmm. So, but in this case, and also actually it's a situation in the general position. If we take a generic C and choose some specific value of delta, then we always have only one submodule, so it's enough to factorize by it. But if C is special, it can turn out that there are two submodules and they also intersect. They itself have their own submodules, and it is a so-called case of minimal models. Mm. So, but in this case, uh, mm, mm, so let me think. Mm. So in this case, this submodule will be irreducible, and also this Verma module without the submodule will also be irreducible. Uh, so. Um, so this is what happens in the general position. So if you suppose that it is irreducible, then so what I wanted to do something else. So mm, we can also ask the following, like what is the relation of this non-trivial submodules to a bilinear form defined on the Verma module. So remember that there is this bilinear form which takes two vectors L minus Kn delta L minus K prime L minus K prime and prime delta. So it's defined in this way. Just take conjugate of this vector, write L Kn and so on L K1, L minus K1 prime and so on L minus K prime and prime on delta. So there's a definition, and we can easily check that if we consider scalar product of L minus K1, so L minus Kn delta times some other vector, some highest vector, then so it will look like delta L Kn L K1 this vector chi. So if we now look at it this way, we can say that the two properties are equivalent. That and this chi is killed by all possible by all positive Virasoro generators. So it's a null vector. So this is equivalent to the statement that chi is orthogonal to everything. Chi is in the kernel of this bilinear form. Is it clear? Because if it is killed by all positive L's, it is clear. When we start to compute this scalar product, we just act with the first L we see, and we already get 0. But in the opposite direction, if it is in the kernel of this form, no, so what should we say actually? No, probably. Sorry, I am actually. I think I'm lying here. There can be some complicated situations when we get some other orthogonal vector. So we should write it only in this direction. Sorry. If you want this equality in the opposite direction, we should say that there are no submodules, and there are no submodules above this vector. So if you get something orthogonal uh, for all possible LKs times chi, then uh, we can conclude that these vectors are zero. So if we know that they are on that levels where our bilinear form is non-degenerate. In general case, probably it's not even true. I'm not quite sure, but probably it's not true. So, but, mm, but could you say it again? Mm-hmm. Mm. So it should be true if we have only one such a submodule, because all these LKs will belong to the level of Verma module where bilinear form is non-degenerate, and so if something is orthogonal to all vectors at this level, it means that it is zero. Oh, or what is mm, mm, the question? Hmm. Yes, if it is non-degenerate on that levels. But in principle, we can have situations when there are Verma submodules of this Verma submodules and so on. So there is a lot of this highest vectors, and um, I'm not sure that it is true that LK's times chi will be zero. Well, mm, oh, yes. So actually, no, I'm just trying to tell you some bullshit. Sorry, because uh, this entire Verma module, this one, is in the kernel of bilinear form. So, no, there is no, there is no such question. Yes, because this entire module is in the kernel. Hmm? No, I'm saying first that this vector chi is in the kernel of bilinear form, and not only this vector, but also the whole Verma module is in the kernel, because if you compute the and and then uh, L minus k1, so L minus kn, prime and prime, acting on chi, also is in the kernel of this bilinear form. Uh, because chi is on the different stage in the Verma module. Chi is some combination of C y is L minus y. It has different dimension. Delta is the picture is the following. Delta is here, and chi is somewhere here. So they belong to different levels in this Verma module, so they are orthogonal just by default. Yes, because like it's in the kernel. It means that it is orthogonal. So for any case, it is 0. L any case, any k prime, L minus k1, L minus kn, L minus k1 prime, L minus k n prime prime, acting on delta, acting on chi. So yes, because we can write it this way. Like we can write that it equals to delta L kn, L k1, L minus k1 prime, L minus k prime and prime, chi. And then we can just move all negative operators. No, so, what should we do? We can yes, we can swap all of them and get some linear combination with but we can get some linear combination with only positive or only negative. No, we can get some linear combination where negative L's stay at the left, minus minus something. Ly acts on chi. And some of these terms vanish because either this else kill delta or this else kill chi. But even if there are no else which can kill delta or chi, it will still vanish because delta is orthogonal to chi. So. This submodule is orthogonal to everything. The consequence of this is the following. If we manage to construct unitary representations of the Versor algebra, for example, embed this Versor algebra into some other algebra, like this one, then we have a guarantee that all these submodules will be factorized out because they are in the kernel of scalar product, and if representation is unitary, then all vectors of zero norm or orthogonal or vectors which are orthogonal to everything vanish automatically. And I would like to consider such an example. Namely, let us consider this free boson case. Actually, we can ask the following. So there is this example of free boson. No, let us first write some formulas. So we had the following formula for the energy momentum tensor. It was 1/2 times normal ordering of g of z squared. By the way, maybe let us discuss this question about the normal ordering now. This normal ordering is the bosonic normal ordering, which comes from QFT, which says that we should move positive modes to the annihilation operators to the right, creation operators to the left, so that it is well-defined object. But there is also a CFT normal ordering. Like CFT versus QFT normal ordering. So if we work with some interacting theory with trivial operators, we don't know how to order them in the general situation. But we can do the following. We can say that if we work with CFT, there exists OP of two operators. B of Z, B of W is sum from k equals to minus infinity, sum n, AB n of W over Z minus W to power n. And let us say that CFT normal ordering is defined like this. We just remove all singular terms and take the first regular one. So let us say that AB normally ordered of W is by definition AB 0 of W. And we can see from this formula, that, for example, if this series contains many singular terms, then AB does not equal to BA. Because we can take the first part of a series and expand around different point. So it will contain some terms of smaller orders. But let us see what is the meaning of this normal ordering in terms of modes. So we can write it in the following way. We can take this term of expansion by computing the contour integral. So AB of W equals to the integral in Z dz over 2 pi I Z minus W, maybe 0 over 2 pi I A of C, B of W over Z minus W. So there is this expansion, but we can also write it. Remember this trick, which we can now use in the opposite direction. So here we have integral around 0. So it is 0, it is Z, and it is W. Oh, no, it is W, it is Z. And we can write this integral as integral over this contour. So it equals to the integral over Z, absolute value of Z is greater than absolute value of W. dz over 2 pi I A of Z, B of W, or Z minus W. Actually, maybe I want to remember that there is a normal ordering everywhere. Minus integral absolute value of Z is less than absolute value of W, dz over 2 pi I. So here also normal order in fz b of w over z minus w. And so now let us expand this denominators in the appropriate regions. So when z is greater than w, we can write that this integral equals to z is greater than w, 0 over 2 pi I of z b of w, and here sum from n equals to 0 to infinity wn 0 over n plus 1. And this other integral, this other denominator can be expanded in the same way. So it is 0 over 2 pi I. Here the order of operators is opposite because of the radial ordering. So maybe let me write it in a different way. This sum is from minus infinity to minus 1. Wn over z n plus 1. So is this one fine? So just a geometric progression. So from minus infinity to minus 1. But now we see that this integral in z can be somehow computed. And namely, we say that suppose both of these fields have some mode expansion. So let us write this. So it is integral over w dz over 2 pi I sum of a n over z to n plus delta of a sum of wn to z n plus 1 here from 0 to infinity p of w plus this other integral. P of w sum of sorry, the summation index should be different. Right? So now the question. What would be the value of this integral in z? What happens if we integrate such an expression? So if so this series contains minus first, minus second, minus third, and so on, all negative powers of z. If we multiply it by something which has a strictly negative power of z, this integral will vanish. So the only possibility to get something on zero is to start from something which has positive power of z. Yes, we see that if you want to write it this way, we should have integer delta. So at this moment, when we want to compute this integrals, because yes. But in our examples, it will be, for example, this energy momentum tensor or this U1 current, so they have integer numbers. Uh, it depends on which fermion. If it is Navier-Schwarz fermion, then it is periodic and everything is fine. So, huh? But the first choice is who is delta, and second choice is what is the range of k's. Because a typical expression for the fermion is psi of z equals to sum of psi p over z to p plus 1/2, when these p's are also half integer. So it's Navier-Schwarz fermion. There is Ramon fermion, which has a expansion over integer modes. No, it depends on which uh, it depends on in which fork module you are working, because it has a charge alpha, which is precisely responsible to the power of z, which stays in this expression. What do you mean? Yes. But it does not know anything about this about the range of these powers, because it is some global monodromy around zero, and the only thing which is important for the statistics is a local monodromy of two fermions around each other. And this local monodromy does not know about the range of these powers. So. I'm saying only that this CFT normal ordering might not always work. For example, it will not work this way for the fields with um, absolutely non-integer modes. So it's not like it does not exist, because if two fields are local with respect to each other, we can define their normal product just by this formula. We only need these powers to be integer. Um, but if you want to rewrite it in some other way, using modes of these fields, then we need uh, to have integer powers. So is it fine? Actually, so so let me think. Probably there might be some way to fix this problem, but no, I don't know. But okay, so if these powers are integer, we see that if you take some z to, if you take some z to positive power, we compute this integral by residue, and we see that this z is just replaced by w, because dz over z over 2 pi I integrates to 1 for the zeroth order term, and to 0 for other terms. So I'm saying that the sum can be written in the following way. So it is a sum for k plus delta a is less or equal than 0, ak over w k plus delta a. Here just a b of w. And here we have sum over k plus delta A. Delta A is greater than 0. P of W A k over W k plus delta A. Right, so do you agree with this? And finally, this can be written as A of W minus B of W plus B of W, A of W plus. So, the end of computation. So actually, these operators, like 1 over Z minus W, are very common for the Riemann-Hilbert problem, and they play precisely this role. They are so if you expand them in different regions, they are projection operators on positive and negative parts of some Laurent series. So and here they play precisely this role. So they took negative modes of A and placed them at the left, and positive modes of A and placed them at the right. And we notice here that negative means that K is less or equal to minus delta A. So, for example, for the Virasoro algebra, negative modes start from -2. -1 counts as positive, so it will be in this part of normal order. Mm. But what do you mean by physical? We just want to write to define this regular product of two operators by taking the regular part of their OP. So we have a guarantee that this operator has a dimension the same as it has a dimension which equals to sum of these dimensions, and it is somehow similar to classical products. And but we also know that it acts nicely on the Hilbert space. And if we see this definition, we understand why it acts nicely, because what can be the problem when we try to act with a product of two operators on some state? So in principle, we have so if we just take A of W, B of W, and act on the on some vector V. So what do we get? We get a plus of W plus a minus of W, B plus of W plus B minus of W. So this term acts by zero. because it contains annihilation operators with operators with positive modes. And this term acts in some way. So we get a minus of W times B minus of W minus of W acting on V, which is nice because both of these operators are sums in, so it is sum of um, B minus K, some W to power K. This is sum up to some shifts. This is sum of A minus K W to power K. So we just multiply operators with a negative mode, multiply by some power of W. So it's some nice series. But what happens if we try to act with A plus? So in this term, we will have, so in this A plus of W, B minus of W, acting on this vector V. This term has a form sum of B minus K, WK. And but this term contains AKs, W2 minus K. Sum to infinity, like from 0 to infinity. And here from 0 to infinity. And it might happen that AK times B minus K times the state gives something not zero for all Ks. And then in this way, it turns out that we need to compute some infinite sums. So we can see what happens in this case. Like what is the problem with writing just G of W squared. So here we can get something like sum from K equals to 0 to infinity of 1 times V. And this is bad. But if you write it in this way, we see that there are no such terms. In one case, this LW plus just acts on the vacuum. In the other case, there is B plus, which kills almost everything, and there is B minus times A minus. And it is, but it is infinite sum in one directions. It's a product of two series in positive powers of W. Infinite negative powers times infinite positive powers. This is the problem. Because even if we don't think, if we don't think about convergence, if you want to work with kind of simplest possible theory of infinite dimensional vector spaces, we should say that vectors which are allowed are formal series in W and W inverse, such that each coefficient is some finite combination of basis vectors. But if we consider the action of these two operators and we try to compute the coefficient in front of W to some power m, we will need to compute infinite sum. So we will need at least to switch to the completion of this Hilbert space. This is formally, but informally, these sums can just diverge, like sum of ones. Mhm. It, yes. Oh, but how can you include them? Here, we can just put z equals to w. So it's like we take a product of two operators, remove everything which is singular. This procedure of remove singular part is not well defined, because why this precise form of singular part? Like we can also subtract something regular, but we fix some way to remove the singular part. And but hmm? Ah, yes, but then yes, yes, of course. So one part is removed in some way, like we just remove this terms from this expansion, and then another part is goes to zero because the points coincide. So so we will just check on this here. So, but you see what is the difference? In the usual week ordering, we uh, 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 placed all positive uh, powers at the left, all negative powers uh, on the right, um, all creation operators on the left, all annihilation operators on the right, and uh, so let me actually write two formulas for comparison. Uh, so here write so it equals to uh, a minus b minus plus a minus b plus plus b plus a minus plus b plus a plus, right? In case of the weak ordering, we are saying that B minus B minuses should stay on the left. Or, no, so all minuses are on the left, or pluses are on the right. But in that case, plus part commutes with plus part, minus part commutes with minus part. Mm. And these terms are the same, they're indistinguishable. This B plus A plus can be written equivalently as A plus B plus. So this, and mm, so if B plus and A plus commute between each other, then it is just the same as weak ordering. Mm. Well, actually, probably I answered some different question. So these operators can be some complicated composite operators constructed from free bosons, right? In this case, of course, there is one trivial way of ordering when we just multiply these operators and take bosonic normal ordering, and it of course will be different from this one because uh, uh, because when we take usual bosonic normal ordering, it will break the internal structure of this fields. So it's like we write formally a product of bosons and then order everything. So it will not preserve this form when everything which belongs to B stays in one place. Actually, we will compute some examples. We will see what is the difference between, for example, bosonic normal ordering and fermionic normal ordering after fermionization. What kind of answer do you expect?
My point is like you prescribe. I mean, we have Greek ordering and we have disordering by complex analysis. And this gives me two different prescriptions to define a composite operator of A and B.
That weak ordering does not know anything about CFT, about operator expansions. If you
Yeah, sure. But for sure, I can use it to define a regularization of the product of theta.
Yes.
We agree on that. Okay, fine. So we have two prescriptions to regularize product of these, and then I take expectation values, and those in principle is gonna be different, and I can measure like expectation values have a direct counterpart that I can measure in laboratory as a response functions or So in the end, I'm gonna see if the Dick prescription or the prescription by contours is the right one to give me predictions, right? If they give me two different answers, right?
Well, they will of course give different answers because if there are some composite operators, then just two different operators.
Yes.
So sometimes one is zero, another is non-zero.
Yes, sure. So like, is it? I mean,
because for example, for example, take energy momentum tensor of a free fermion. So T is psi, well, 1/2 psi d psi minus d psi psi. And if you take and there is there is an operator which can be computed in any CFT. It is T times T, normally ordered. But if you try to compute this T times T in this free boson theory and use just ordinary weak order, and it will be trivially zero because you will compute psi squared of z normally ordered. Like t times t is non-zero, but t times t normally ordered will be trivially zero, right? And but this operator can be computed. We should take t, multiply by other t, compute this operator expansion, take a regular term, and it will be some operator which is actually also bilinear infermions. And if I remember correctly, it will contain d squared psi or something like that. And the codine of t squared is 0. Yeah.
Does this, okay. So, in principle, which regularization should I choose?
CFT 1. Because if you work with CFT regularization, you have some kind of security guarantees. For example, if you know that original fields satisfied some correct OPs. For example, if you take G, which is realized using fermions, but it is, for example, well, if you take this G, uh, uh, which is psi star psi, so we'll come to this later. But if you take this G, which is constructed in terms of fermions, you can compute the OP of this G, and after this you don't care how it is constructed. You can construct energy momentum tensor just like T equals 1/2 G times G. And you will be sure that it satisfies Virasoro OP. But if you want to, but if you write this fermionic normal ordering for some reason, then you will immediately get this problem that in this case just t itself will be 0. So if you use this kind of low-level normal orderings coming from free field realization, you can break everything, break all the OPs. But if you work with a CFT definition, you don't care about the internal structure. Like you don't care if it is constructed from fermions or it is initially some bosonic field. You also don't care about the structure of the modes expansion of this psi. For example, you can make non-integer mode numbers. And so we should always use this safety normal order to write all the definitions. But after this, if you want some nice computational formulas, we can just take the definition of the normal order and then compute the OP of these fields using, for example, fermionic or bosonic normal orderings to have some expressions which act on the Hilbert space in some nice clear way. But I will actually show such examples of these computations. with different normal orderings. Now I just wanted to tell that there exists this definition, and it works this way. So, is it fine? Or, mm, so, okay. So I was writing it just to say that uh, we can use this normal order to define to write down the energy momentum tensor. So in this case, these two normal orders coincide. It is the same as 1/2 of g times g, and it equals to sum over n and m, 1/2 of an times am, when this normal ordering means that positive a's are on the right, negative a's are on the left. 1 over z to n plus m plus 2. So we conclude that the formula for Verma generators is sum of n plus m equals to k, an times am. 1/2. So in particular, L0 is 1/2 of A0 squared plus sum from k equal to 1 to infinity a minus k ak, the operator of a number of particles times k actually. So who is then L minus 1? So it is maybe better to add this. So we have two terms, A0, A minus 1, and A minus 1, A0. So actually, we don't need this normal order in all other terms. So because the separators commute in all other cases. Maybe better to write it like this. 0 plus and so on. Mm, Probably it is also mm, good to see who is L minus 2. This L minus 2 is mm, 1/2 of a minus 1 squared plus a minus 2 mm, a 0 plus a minus 3 a 1 plus and so on. So I'm interested in this three operators, and because this one is of course L0, the Greek Countable operator, this L minus 1 should correspond to the null vector, and this operator should generate a state which corresponds to an energy-momentum tensor by the operator state correspondence. Mm. So uh, now, uh, what 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 do we do? We maybe erase this blackboard. Mm. And in general, we can also notice the following thing, that if you look at some L minus k, uh, L minus k, it contains A0, A minus k, uh, plus some other terms. Uh, so, uh, mm, mm, so what I want to tell now, let us consider a Verma module with delta equals to 0, which corresponds to the identity operator. And what do we have from a bosonic point of view? We have mm, we have a highest weight state which is just 1. We have a minus 1 in this. We have a minus 1 squared, a minus 2, and so on. And this is a unitary representation of the Verso algebra. Because there is a non-degenerate scalar product on this fork module. But now, so it will be some sum of Virasoro irreducible representations. So now let us try to see what is the action of the Virasor. Namely, let us act by L-1 on this state. L-1 acting on a vacuum is A-1 A0 plus A-2 A1 plus and so on. And action on vacuum. And this just vanishes because A0 is acted by 0, and the annihilation operators kill this vacuum. So here we go. This L-1 just kills a vacuum, and we don't get the state. So we now have a highest vector 0. And the next operator to act on this vacuum is L-2. 0. It gives what? It gives A-1 squared. Vacuum, and that's all. So the second so this second state should belong to a submodule of the Virasor algebra. So the structure is the following. There is this like H1 is a span of L-2, L-3, and so on. Maybe no, how to write it better? Like some polynomials of L-2, L-3, and so on, acting on vacuum. Plus the same acting on this the state corresponding to A-1. Oh, not the same, but the full Virasor algebra. On this. And what are the states in terms of operators? If I remember operator state correspondence, so this one is just identity operator. This one A-1 squared. It is energy momentum tensor, because it is a L-2, and also the fact that we have here A-1 squared is oh, sorry, I forgot to tell who is this A-1. This A-1 is J. So is it clear why it is J? Hmm? Well, we have exponential of dimension 1, for example. Of course, it's not in this module, but uh, oh, we can ask what it means technically. It means that we take J of z, uh, uh, act, acted on a vacuum and took the value of the section at 0. And this is precisely this component at n minus 1, which survives. And this is, so if you put J of 0, we will get this state. And this n minus 1 squared reflects the fact that g is reflects the fact that t is j squared. And this operator is t of z. So the Hilbert space maybe not. It's maybe better to say not delta equals to 0, but a0 equals to 0. So in this case, this a Hilbert space decomposes as this vacuum Versor Verma module and some normal Verma module about the field of dimension 1. And let us check the character of these modules. So we know that in the left-hand side it is a product of 1 over 1 minus q to the k, from k equal to 1 to infinity. And here, this one is a product from k equals to 2 to infinity. 1 over 1 minus q to the k. Plus, here we have dimension 1, so we put here q, maybe better to put it this way, q over 1 minus q, product from k equals to 2 to infinity, 1 over 1 minus q to the k. And now just take sum of these two terms. 1 plus q over 1 minus q equals to 1 over 1 minus q. And we see that it is actually consistent. By the way, we started the investigation of this boson case from the field phi, which had a logarithmical p with itself. Let us try to think what is the role of this phi, what is the nature of it. So let me check the it works. Yes. Mm. 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 Maybe right like like this. So its OP with itself was 5Z 5W was minus logarithm of Z minus W um, minus the same with complex conjugate. So let us consider the OP of T of Z with 5W. So it is minus 1/2. So it is 1 over Z minus W d5Z. Oh, actually, no, probably. Uh, no. Uh, Sorry. This field is fine. I I thought for some reason that this should be an example of logarithmic field, but probably no, it's not that one. No, it's different speculation. So the OP with T in this case is nice, but if you try to compute OP with G, uh, like G of Z uh, times phi of W, it equals to um, probably minus I 1 over Z minus W. So if you look at this, it uh, it tells us that A0 acts non-diagonally on this phi, namely A0 on phi gives minus I times 0. So if you want to ask about the role of uh, this phi, then the answer is that yeah, and A0 acting on this vacuum is just 0. So in principle, this theory contained also this field phi, and we can try to include this. So in this case, there will be a kind of another Verma module, and this A0 will act by a Jordan block. It will map phi to 0 and 0 to 0. And if we also allow some powers of phi, then we can get this Jordan block action not only in A0 but also in L0. And it is called logarithmic representations of the Virasoro algebra. So, for example, if you consider here phi, if you consider here phi squared, then mm, we will have normally ordered. Actually, I didn't want to compute this. But the point is that we can also get representations where L0 acts as a Jordan block, and sometimes are useful, but in a general situation, people consider representations where L0 acts diagonally. And in particular, we are not interested in fields like phi squared, in this case of free boson. Oh, but actually, no, actually, let us compute this OP. Like minus 1/2 When we compute this pairing, it gives minus. Mm, so for there are two ways to pair them. So it is 1 over z minus w squared times nothing plus z minus w. Yeah, we have such LP with the field have w squared, and what it means. So this term is L0. So it tells us that L0 acting on this phi squared is minus, maybe I write this state as state of, no, maybe just vacuum identity operator. Mm. And like L minus 1 on phi squared as always equals to d phi squared. So you see there is there is an example when L0 x on phi squared is gives a vacuum, and L0 on this vacuum, as we know, gives 0. So L0 is such a block, and there on this there's a stage. So if you consider this free boson and allow not only powers of derivatives but also powers of fields, we will get a logarithmic representation of the universal algebra. But it is only for those who likes logarithmic representations, because usually people avoid this and consider only such operators like J and T. Initial.
When you compute the UP of J with phi, and you got minus I, that one, yes.
Mm-hmm.
Then it means that A of minus 1 on phi is minus I.
No, it's A0 because expansion of this expansion of a field starts from z to minus delta times A0. So g of z n to z n plus 1.
And similarly, from the first OP, we get that phi was J, right?
Yes.
So we extract the power of P with the coefficient of minus 1, and that L something which I don't know, applied on phi gives me Z.
Yes. If I want uh, to add something to this picture, so yes, we should add this other module with phi, squared, and this state which was not obtained by the action of L minus 1 on this vacuum will be obtained as the action of L minus 1 on the other vacuum on the of this field phi.
But the field phi is not, I mean, I can find it already within that age, right? Because it's not a prime.
It is a primary. It is a primary for the Virasoro algebra.
No,
So, hmm?
but it doesn't correspond well under change of coordinates, right?
L minus one, a minus one on 0.
No, no. I'm saying the phi, the field phi, phi.
Mm-hmm.
The field phi is not a primary because when I change coordinates, you get a Schwarzschild derivative, no?
No, field T is not primary. Field phi is some. Well, I don't know how to characterize it correctly. Uh, because it is a kind of field of dimension 0, but but it is different from the identity operator. Uh, so
But I mean, isn't it an assumption of CFT that the only operator with zero dimension is the identity? Or every only primary operator with dimension
yes, there is such an assumption, but here this field is quite bad. For example, if you create some state using this field, it will contain zero mode, and so it will be a wave function proportional to phi 0. And it is not normalizable, so we will need to integrate phi 0 squared over the real line. So mm, well, also, if you add this phi and allow all possible OPs, we will necessarily get this operator phi squared, which is the logarithmic field, such that L0 acts by non-zero operator on it. So, mm, so it is something not nice at all. Actually, so that there will be a problem with action of O0 also on this phi, but no, now I see that it is fine. Is it? Yeah. Oh, okay. Sorry, it's already 8 past 18. Oh, sorry. I can only say that these operators containing just powers of phi are pathologic. Mm, because uh, because both A0 and L0 start acting non-diagonally on such states. So, and it is related to the fact that OPs of these fields contain logarithms. And mm, people usually don't like to consider this unless they're interested specifically in the logarithmic CFT. So, so are there any questions about this? Okay, so maybe then uh, mm, that's all. Next time, I will go back to general formalism and tell about the conformal blocks and how to compute them. And then we will study some other systems with conformal symmetry. Okay, so thanks for your attention. Bye.